Hello, this video will be about logarithmic functions as inverses. So we're starting with the notion of how an exponential function works. An exponential function, we'll recall, has this graph that is almost perfectly horizontal on one side and then grows. Let me draw this a little bit better. But even though it's almost horizontal, it's not literally horizontal. And as we move along this graph, all of these points actually have slightly different y values, which means we have a one-to-one function that has an inverse function. So the exponential function can be reversed. And simply by definition, a logarithm is the mathematical operation that reverses what exponentiation does. So here's our definition. Assuming we have an eligible base, so a number that's positive but not 1, the logarithm base b, always say the word base, logarithm base b, is defined to be the operation with this property. Saying log base b of x is equal to y actually is just the same meaning as saying b raised to the y power is x. You can abbreviate this with just log. So this might take a little bit of time to get used to, but once you know what it means, it's usually pretty easy. Either you can figure it out quickly or you're allowed to have your calculator. So if we have log base 2 of 16, right, let's just give this a name. Let's call this y. What this means, so feel free to write this out until you really master it. This means the same thing as saying 2 raised to the y power is equal to 16. When we're taking a logarithm, we're basically undoing the exponentiation and trying to figure out what was the power. That's the thought process here. What's the power of 2 that gives us 16 as the answer? And maybe you can do this instantly. Feel free to just experiment. 2 times 2 is 4. 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. So that's 2 to the 4th power. So this is equal to 4. 4 is the power that we need to raise 2 to that power and get 16. So just a couple of warnings. Logarithm is a brand new operation. Sometimes people will look at this and they'll just say like, oh, how many times does 2 go into 16? And they wind up dividing and saying 8. This is not division. Really make sure you are pausing to think, what power do I have here? Feel free to write out something like this. Really remind yourself of its meaning. Do a little computation if you have to. And the thing that makes things a lot easier is remember when you're switching back between logarithms and exponential forms, the base is always the same. So it's the other things that switch roles, but the base is the same. So with that in mind, try figuring out these handful of logarithms. Hit pause and give them a shot. I'll warn you, you need to be comfortable with fractional and negative exponents. All of these are doable without a calculator, but you may need to be slightly creative about your exponents, and one of them doesn't have an answer. See if you can figure out which one. Okay, so I hope you have paused there. So, oops, oh, that's the wrong thing. For this one, we're thinking base is 3. 3 raised to which power gives me 9? That's my thought process. All right, well, 3 times 3 is 9, so it's the second power. Here we're thinking 10 raised to which power gives us 1,000. That's 10 times 10 times 10. So that's the third power. And one thing I'll point out is we have a decimal numerical system in which 10 is one of the most important numbers. So because of that, there's something known as the common logarithm. If you just see log and nobody writes the base, you may assume the base is 10, and so that would be 3. So a log without a base means base 10. Okay, here we're thinking 2 to which power gives us 1/2. And this is where we remember, oh, how do I get fractions? I get fractions with negative powers. This is definitely going to be some negative power. But we really just have 2 to the 1st in the denominator. So this would be 2 to the negative 1. 2 to the negative 1 just means 1 over 2 to the 1st. Log base 9 of 1, we're asking ourselves which power of 9 gives us 1 as the answer. And hopefully you remember, you can take it as a definition. A base raised to the 0 power is equal to 1. So this is the 0th power. Log base 9 of 3. So 9 raised to which power is 3? So it's not negative because we're not getting a fraction, but it's not a whole number power, right? 9 to the first is already 9. So that might make you think, oh, it's a fraction. And fractions are roots. So we know the square root of 9 is equal to 3. And hopefully you remember that a square root is actually just the same as the half power. So this is 1/2. 9 raised to the 1/2 power is equal to 3. For this one here, we're thinking which power of 2 gives us 32? And maybe you don't have that memorized, but you can experiment. 2 times 2 times 2 times 2 is 16, but 1 more is 32. So this is the 5th power. For this one here, we want to notice that there's just a pattern of cancellation. We don't really need to know what this thing is, because it's basically saying what power of 4 gives us 4 to the 12th power. Right? If we did this thing with a question mark, which power of 4 gives us 4 to the 12th power? So we don't need to know what 4 to the 12th power is. We simply know this is 12. When we have a logarithm and an exponential with the same base, because they're inverse functions, they will cancel each other out. It would work also in the other order. If I had something like 5 raised to the power of log base 5 of 100, I don't even need to worry about what log base 5 of 100 is. Power base 5, log base 5 back to back, they cancel each other out, and the answer is 100. And finally, for this last one, we're thinking which power of 3 gives us -3 as the answer. Now, it's not a whole number. It's not a fraction. Fractions would give us roots of 3, not negatives. It's not a negative power. That would give us a fraction. And it turns out there's just nothing that works. So this does not exist. It's simply an impossible operation. Because if we were to graph y equals 3 to the x power, -3 would just be nowhere on that graph. Our graph looks something like so. Y equals -3 is down here, and there's just no place on the graph of that function where the answer y is -3. So you can say undefined, does not exist, anything that communicates that this is an impossible operation. So that's not a special property of -3. We can only take the logarithm of a positive number. You can think of this as an issue of domain. You can take a logarithm of any positive number, might need your calculator for it, but you can't take a logarithm of 0 and you can't take a logarithm of a negative. Now, why do we care about logarithms? 2 reasons. From a practical point of view, they are helpful for measuring certain kinds of phenomena where the numbers might otherwise be overwhelming. So pH has to do with number of ions in a solution. The numbers are so big we can't wrap our heads around them, but a logarithm helps us understand it better. Same with earthquakes. When there's motion in an earthquake, some are so much bigger than others, but it's hard for us to really wrap our heads around that. So Richter scale uses a logarithm to make it easier to compare them. Logarithms are also really helpful because they're built into the calculator and they let us solve equations that have exponents in them. So here's an example. If I wanted to solve this equation, 3 times 1.07 to the x equals 15. Here's what I could do. Right off the bat, I could divide by 3. We'll practice more of this in the next section. But we get the exponential expression all by itself. Every exponential expression can be rewritten as a logarithmic expression. So this is the same as saying the logarithm base 1.07, that feels awkward, but it's going in our calculator, of 5 is equal to x. On your calculator in blue next to the digit 1, it says log. So you use control and you type that, and then it prompts you to put in the base at the bottom, and then the argument after that. So you can just create this on your calculator, and the approximate answer here is 23.788. Like so many tricky things, sine, inverse sine, square roots, powers, logarithms are built into modern calculators. So simply knowing they exist allows us to solve equations like this. Now, let's just talk briefly about graphs. This might be helpful on your contours project. Let's assume the base is greater than 1. And most of the time when we are applying logarithms, we're applying them with a base that is greater than 1. So log base 2, log base 3, log base 10, they all have a very similar picture. And it's actually the same shape as the exponential graph with a change in orientation. So you could play around with this on Desmos, but I'll just show you what it looks like. We're going to have a graph that only exists in the second and first quadrants. So along the negative y-axis, it's following really closely. This part of the graph is not literally vertical, but it's extremely similar. Then it flattens out. One really easy point on this graph will be 1, 0, regardless of what the base is. Another really easy one would be b, 1. Right? So just plugging into this formula, if x equals 1, we have y equals the log base b of 1, which is 0. If x equals b, we have y equals the log base b of b, which is 1. So those are our easiest points. And just to comment on this graph, a couple things we might know. The domain is x greater than 0. There are no places on this graph where x is equal to 0. There are no places on this graph where x is negative. Right around here, we have what's called a vertical asymptote. So the graph follows the y-axis at the bottom. This is called asymptotic behavior. It's not literally a vertical line, but it's really, really close. And then out here, it grows slowly. It does keep growing. It does not get horizontal. If you did this on Desmos and zoomed out, you would notice it keeps going up and up and up and up. It's just very pokey about how fast it does so. So maybe you'll have a little bit of homework where you're playing around with this graph and the transformation rules, but it's nice to keep this in mind. If you're trying to match this for your contour project and you have something that's nearly vertical and then growing kind of slowly, a logarithmic graph might be what you want. But that is it for this section.